also
very
pleased to have Guowu Meng, and he's going to tell us about generalized Kepler problems.
Okay, thank you. Thanks for coming. What I'm going to report is discovery about the Kepler problem and Euclidean Jordan algebra. The two things are similar and related, but actually they're deeply related. Hi. Okay, so I will start with a general remark. Say for any elegant example, we wish to find a theory behind it and understand why it exists in the first place. Of course, these two issues are related. And finally, we want to explore the consequence in math and physics. And I would argue that in this talk that the Kepler problem serves as an elegant example, such an elegant example. Here's my talk plan. First, I will introduce the Kepler problem. So those are the important names associated to this problem. So Newton, of course, I think most of you know some history about it. So Newton introduced this problem classically, and Schrödinger introduced this problem quantum mechanically. And Laplace, Range, and Lenz, they discover the extra large symmetry called Lenz vector nowadays. And Pauli use this extra large symmetry to solve the quantum mechanical problem algebraically. And Fock made the symmetry more explicit. And those two physicists, they discovered something new. Namely, this Schrödinger problem has to do with the conformal group of our Minkowski spacetime, SO24. Okay. A kind of a mystery. Next, I will talk about the general Kepler problem in its early period. So those are the important names associated to it. And then I switch gears and to talk about something similarly unrelated, namely the Euclidean Jordan algebra. And those are the important names associated to it, and von Neumann was a faculty here. And finally, with this Jordan algebra introduced, I can talk about the generalized Kepler problem in the most general fashion. Okay, let me talk about the Kepler problem first. So as you know, the Kepler problem is a physical problem about two bodies which attract each other by a force obeying the inverse square law. And the two bodies could be either the sun and a planet, or the nucleus and the electron for the hydrogen atom, the simplest atom we have. By the way, the two-body problem can be reduced to the one-body problem. So essentially, it's a one-body problem. And there are three main mathematical aspects. The first one is a classical dynamics problem. And the next one is a quantum bound state problem. The third one is a quantum scattering problem. For the classical dynamical problem, the main mathematical concern is the description of trajectories as algebraic curves. And it is easy to show that a Kepler orbit is a conic. So by Kepler orbit, I really mean a non-colliding trajectory. The two bodies could collide each other. That kind of trajectory I'm not interested in. So I'm interested in the Kepler orbit. Okay. So here is the picture. If the energy of the system is less than 0, you have bound orbit. That is an ellipse. This is the sun. Okay, roughly is the sun. Okay, should be the center of the mass. Okay, and if the energy is equal to 0, then you get this parabolic orbit. If energy is bigger than 0, you get this hyperbolic orbit. So in any case, you have a conic, but you have different description in the three different cases. To find it, so here is a short demonstration which should appear in the math textbook. To find the orbit, we start with this equation motion. So this is really F. This is the force, gravitational force. This is ma. So I'm doing mathematics. So I set all the physical constant equal to 1. Okay. And then we observe that angular momentum is conserved. It means independent of time t. For any central force, here is not necessarily 3. This is always conserved. But what's amazing about this central inverse square law is you have additional conserved quantity, namely this A vector, this L cross product with linear momentum, but mass is 1, so it becomes velocity, plus the unit vector of the position vector r. So r is the position vector, and this r, scale r, is the length of the unit of the position vector. Okay, it's just a simple computation. You take a derivative of that, then this constant space is double derivative here. Double derivative here can be replaced by this, and then take a derivative there. Then you compute, it becomes 0. Okay, so as a consequence, we can derive the orbit very quickly. So you take a dot product with r, start from here, take a dot product with r. So since r, a is a constant, so its length I call it a. Okay, and suppose the angle between r vector and a vector is theta, then r dot a would be this. Okay. On the other hand, if you take this side dot with r, like this unit vector dot with r, just the length of r, and here you have that. Then this is a triple product. You do cyclic permutation, and then you end up with L squared. L squared means L dot with L. Okay, and this R here, this R here, so algebraically you can easily solve. You get this, and this is really the conic written in the polar coordinates on the plane. Okay, in the case a equal to 0, this r equal to constant. By the way, for the Kepler orbits, non-colliding trajectory, this L is never 0. Okay, so if a equal to 0, this r equals to constant, you get a circle. In general, a between 0 and less than 1, you get an ellipse. A equal to 1, you get something called parabolic. And a bigger than 1, you get a hyperbolic orbit. Okay, there's another observation I want to make, namely, look at here. If we understand the meaning of cross product, then we know immediately this r vector is perpendicular to L. But since L is a constant, so r is perpendicular to it. So r is really on the plane perpendicular to L. So trajectory is a plane curve. Okay, and another fact is this L and A are perpendicular to each other. In fact, each term is perpendicular to L, because this L cross R prime is perpendicular to L, and here this R is perpendicular to L. Okay, so A dot L equal to 0, and this absolute the length of A is really the eccentricity. And then what's the direction? Well, it's for the conic you have two focus, and you draw a line segment from one focus to another focus, and you get a line segment, and this A vector is parallel to it. Okay, so you would say, we would say this A vector is the eccentricity vector. Okay, so A and L are perpendicular, and A is the eccentricity vector. Okay, now I want to talk about the hidden symmetry. There's an obvious SO3 symmetry because of the central force, and there's something called Nezer's theorem, which say whenever you have symmetry, you have conserved quantity, and vice versa. And here you have the L is the angular momentum. It has 3 components. It will be the generator of this SO3. SO3 is a 3-dimensional Lie group. And then you have the actual symmetry is SO4 because we have both L and A conserved. So A has 3 components, L has 3 components, altogether 6 components. And the SO4 locally is a 2 copy of, Cartesian product of 2 copy of SO3, so it's 6-dimensional. So here exactly 6. Okay, and this system is people called super integrable in the sense that the number of function independent conserved quantity is bigger than the degree of freedom. In this problem, the degree of freedom is 3, but the number of independent of conserved quantity is 5, because 3 from L, 3 from A, but you have to subtract 1 because L dot A equal to 0. That's one constraint. We have to subtract that condition. So 5 greater than 1. Okay, super integrable. Now let's go to the quantum bound state problem. And here are the main mathematical concerns. The first, we need to determine the bound state energy spectrum. And the next question is to describe the corresponding energy eigenspace as a representation of this SO4 group. And finally, there is something called a Hilbert space bound state. Namely, you have lots of energy eigenspace. You take a direct sum of them, then you take an L2 completion of it. You get a Hilbert space. That Hilbert space is called Hilbert space bound state. And that thing turned out to be unitary lowest weight representation of this SO24. And that thing is this is a discovery of Clannad and Barrot in the 60s. Now here's the answer to these three questions. The bound state energy spectrum is a negative 1 over 2n squared. Here n is a natural number, runs through all natural numbers. And the nth energy eigenspace is the tensor product of two identical copies of the n-dimensional irreducible representation of SO3. Remember I said that the SO4 is a locally isomorphic two copy of SO3. Okay, the irreducible representation of SO4 would be tensor product of two irreducible representation of SO3. But then remember there's a condition A dot L should be 0. And that condition really says the two copies of SO3 irreducible representation should be the same. So it has to be identical. So as a consequence, the dimension of this nth energy eigenspace is really n times n, which is n squared. In particular, n equal to 1, it's just 1. So it's non-degenerate. The ground state is non-degenerate. Now, as a representation of SO2, 4, the Hilbert space bound state is a minimum and off-scale type. So what do I mean by the minimum? In representation theory, people know that this representation is associated with the orbit. And this co-adjoint orbit. This co-adjoint orbit has the smallest positive dimension. And what do I mean by scalar type? In terms of physics languages, that means the ground state is non-degenerate, okay, not high dimensional. High dimensional is called a vector type. Now, the quantum mechanics mass model is that in quantum mechanics we promote all physical observable to Hermitian operator. So in particular, the energy will be promoted to Hamiltonian operator. So this one. So this first part is the kinetic energy. The second part is the potential energy. So this delta is a Laplace operator. And what do you mean by bound state energy spectrum? Well, first of all, it's a real number lambda such that this equation is true. This equation has a non-trivial square integrable solution. Non-trivial means not identical 0. Square integrable means the integration, take absolute value square of this, integrate against the Lebesgue mirror over the whole R3 should be finite. Okay, square integrable. If you pick a random lambda, the only solution you have, square integrable solution you have is 0, is a trivial one. Okay, so this lambda has to be a special one. And the quantum scattering problem, the main concern is to determine the scattering amplitudes as meromorphic function of energy. I won't talk much about it. By the way, this is also related to the bound state spectrum problem because this meromorphic function has poles. It poles exactly at the bound state spectrums. Now, we'll talk about the generalized Kepler problem in its early period. As with many elegant examples in mathematics, one naturally wonders whether the beautiful Kepler problem is an isolated problem or not. It turns out the Kepler problem has a vast generalization, just as the Euler number has a vast generalization. Here is a prehistory. First, there is everyone's generalization. We replace R3 minus the origin by R to the n minus origin, while still assuming the inverse square law. Then the system is still super integrable. But there is an interesting one, which is non-trivial to me. That is by adding magnetic charge. And those two independent groups discovered this toward the end of the 60s. So basically say, if I use a hydrogen atom as a model, so the nucleus, you assume it's a diene. That means carry both electric charge and magnetic charge. In the real physics, the hydrogen atom just carry electric charge, magnetic neutral. But hypothetically, we're doing mathematics. We hypothetically supposed to carry both magnetic charge and electric charge. So it's called diene. But then so-called the scale, we have the scale potential come in to the picture into the Laplace operator, and the vector potential, okay, coming to the Laplace operator. But at the same time, we have to adjust the scalar potential like this. This is the inverse square law. We have to adjust this to that, okay? And here mu must be half integer, and this is magnetic charge. This direct quantization tells you it has to be like that. And there's a topological reason because it's twice of mu is the first term number, so it has to be integer.
So the magnetic monopole charge acts like an angular momentum, basically. If you just go with a regular 1/r
Yeah. This is the extra part. Yeah. We can find this by, well, one way to do it, you eventually you go to the ODE. You want the ODE to be, there's a truncation because the final solution polynomial. Then you will pick, you will be forced to choose this kind of terms. Okay. And then, of course, there's a natural question. Remember, we have the high dimensional analog of the Kepler problem. We also have a magnetized version of the Kepler problem. So naturally, you say, combine these two. Can we add magnetic charge in high dimension? That's a natural question. And the answer is yes in dimension 5. That was done in the 90. And they, in the original 3 dimensions, they use a Dirac monopole. But in this 5 dimension, they use something called a Young monopole. This Young is a famous C.N. Young, who was a faculty member here before. Okay, he in the 78 he generalized the Dirac's work to the 5-dimensional cases. But then I realized that this can be done in any dimension if we use a so-called generalized Dirac monopole. Because in the early work they thought this existence of a monopole has to do with the division algebra. The Dirac monopole has to do with the complex number. Young monopole has to do with quaternions. But then we don't have many division algebras, so they thought we should stop there. But I realized the whole problem has to do with the spin, which has to do with the Clifford algebra. So not only in the odd dimension, like 3 and 5, you can also have spin in even dimension. Okay, in any dimension you can have it. I'm doing this problem because partially I want to justify my generalized Dirac monopole work to make sure this really makes sense. Okay, it turns out everything can be done successfully. Now, is this the end of the story? No, far from it. The clue comes from the following 2 naive questions. The first one is to find a geometrically simpler description of the Kepler orbits as conic. In the original conic, we have 3 cases. To me, this is not simple enough. Okay, it's not unified enough. We will have an even simpler picture of our conic. The next, to understand why this SO24 enters into picture. To me, it's a mystery. It turns out these 2 problems are really related. So first, I will start with the ancient Greeks' definition of a conic. So by that definition, a conic is a curve, well, not straight things, it's curved, obtained by intersecting a cone with a plane. So here is a picture. Okay, so we are in a 3-dimensional space-time. So 2-dimensional space, 1-dimensional time. And here is the cone. This is, to physicists, this will be called future light cone, and this is past light cone. And if we take any plane, we will do the intersection. If we get a curve, that curve will be a conic. Connect to the picture we had already. That really means we have to do the projection of this whole thing onto the horizontal plane. And that will be the Euler picture of a conics. Okay. By the way, this cone, with this cone point removed, is a smooth space, 2-dimensional space. It's diffeomorphic to R2 minus the origin. Okay, because this is really the graph of the function t equal to square root x squared plus y squared. Away from origin, this function is smooth. Okay, so then this description is much simpler and much uniform. By the way, suppose we take a plane contains z-axis and also this x-axis do the intersection. What do we get? Well, it will be part of like a half line. But this half line is really correspond to the colliding trajectory. So this way, you really can get all kinds of trajectory, not just the non-colliding. The colliding one, you can also get it. And it's a very uniform description. Just take any plane intersect, you will get an orbit. Now, the actual things, actual space-time is 4-dimensional. In the Minkowski space-time. So here's my observation. So there's it's called light cone reformulation. So it is more natural, in view of a previous slide, it's more natural to view the Kepler problem as a dynamic problem on the future light cone with the cone point removed. Okay, inside the Minkowski space. It's a 4-dimensional, 3 plus 1 dimensional. Okay, and this explains why SO24 should appear, because this SO24 is the conformal group of this guy. well, conformal compactify. Okay, as the Lie algebra of this guy acts on this. Okay. Now, this new perspective opens more doors for the search of generalized Kepler problem, because Minkowski space is just one example of Euclidean Jordan algebras. There are many, many of them. Okay, and so let me remind you the key to the generalization. So just as vector bundles are the natural home settings for characteristic classes, Euclidean Jordan algebra as a natural home setting for the generalized Kepler problems. And moreover, one discovers more superintegral model even if one just sticks to the Minkowski space. Okay, let me go back to this picture. I say this future light cone is associated with our original Kepler problem. And there is a piece inside bounded by this future light cone. That thing will be also associated with a superintegral model, and that thing is really new. Okay. Now, let's talk about the Euclidean Jordan algebra. First of all, it is a finite dimensional. We are only interested in the finite dimensional one. Okay, it's a finite dimensional real algebra, and it's a commutative. Okay, and with a unit. Such that the following two conditions are satisfied. The first one I call the weakly associative. For associativity, normally we have three elements, A, B, C. The product in two different orders always the same. Okay? But here we have A, B. The third element has to be A squared. So it's a special kind of associativity. Okay? And the second part is the formula real. For two real numbers, A squared plus B squared equals 0, and both A and B has to be 0. But here we call the formula because it's just elements. Okay, so A squared plus B squared equals 0 implies this. Okay, how do we understand this? One way to
A, B, the generators?
A, B are element in the algebra.
Any elements?
Yeah, any element. Yeah, not necessarily generators. Yeah. So I would try to say this is really Jordan algebra is really. By the way, if you just stick to property 1, it's called Jordan algebra. The property 2 it gives you Euclidean. In the old days, people called it formally real. When Jordan and Wigner they did the classification, they called it formally real because this condition is a formally real condition. And why it becomes Euclidean? Because this is equivalent to another condition, which says this finite dimensional real vector space has a unit product structure there, such that this unit product structure and this Jordan multiplication structure are compatible in the sense that the multiplication by A is always self-adjoint with respect to the unit product. So this condition is equivalent to that condition. So that's why nowadays people call it the Euclidean Jordan algebra. So I think most of you mathematicians are familiar with Lie algebra. So I will say this is the analog of Lie algebra. In the Lie algebra case, suppose we talk about real Lie algebra, and there the product is a skew commutative, AB equal to negative BA. Okay, so I would say it's a super analog of that. And then there's a Jacobian identity. It's a replacement for associativity. So here I use this weak associativity. Okay. And then, in fact, for the real Lie algebra, there is something called a semi-simple and a compact real Lie algebra. And this is compact and semi-simple part correspond to the second condition. So in some sense, this Euclidean Jordan algebra is the simplest kind of a Jordan algebra. Just like the semi-simple compact Lie algebra is the simplest Lie algebra, just like that. Okay, it's always semi-simple. By the way, this is condition always implies semi-simple. By the way, there is an analog of Cartan killing metric in this case, which is always positive definite. Okay, so become the inner product. Okay, so it decomposes into a dark sum of simple one. The simple one admits invariant inner products, which are unique up to multiplication by a positive number. Okay, now here is a classification. It's in the 30s, done by them. The first one is the collection of all real numbers. But in this case, actually, the algebra is associative. In all other cases, non-associative. And this one is really the Lorentz space. This is the time, this is the space. And what is the product here? you take any two things here, the product will be the dot product, will give you a number here. You take a number here, take a vector here, the product will be a scale multiplication, so end up with a vector here. You take any two real number here, with multiplication, just the ordinary real number multiplication, end up with an element there. And then what is this? This is the n by n real symmetric matrix. And then what is the multiplication? It's a matrix multiplication, but then symmetrized. If we take two real n by n symmetric matrix, we do the ordinary matrix multiplication, then we end up with, in general, a non-symmetric matrix. But if we symmetrize the product, we end up here. And here, similarly, we take n by n complex Hermitian matrix, and here n by n quaternion Hermitian, here n by 3 by 3 octonion Hermitian. But here we have the n at 3, because if we would go higher, like 4 or 5, then this won't be a Jordan algebra. Of course, we can go back to 2, H2, but that is okay. But then that is isomorphic to r plus r to the 9. So similarly here, I restrict n star from 3, because n equal to 2, each of them is isomorphic to one of the guy here. So this is a complete list. And this one I highlighted because this is really the simplest one, and also it's a associative. And this one I highlight because this one people called exceptional in the following sense. Jordan algebra, just like Lie algebra, has something called like universal enveloping algebra. So it has to do with associative algebra, right? Start with associative algebra, you do anti-symmetrization, you get Lie algebra. And all this have something like that, but except for the last one. The last one is not associated with associative algebra. So that's the difference between Jordan algebra and Lie algebra. Okay. By the way, those are uniquely determined by two things. One is called the rank, another is called the degree. What do I mean by the rank? For this matrix type, the rank is really this n, and this 3. And for this case, by the way, this is really can be viewed as special case, n equal to 1. So this case, the rank is 1. For this case, the rank is always equal to 2. Okay, and then there's something called degree. The degree in this case, for n by n matrix, there's an off-diagonal entries. The off-diagonal entry is a real number, so it's 1. And here the off-diagonal entry is a complex number, so viewed as 2 independent real numbers, so you get 2, so degree is 2. So similarly, here's a degree 4, and this is degree 8. And the degree here is n minus 1, okay? And so if we, any Jordan algebra is uniquely determined by this 2. And in the case rank equal to 2, you have infinite many. In the case rank equal to 3, we have 4. In the case rank bigger than 3, we have only 3. This is something like the regular solids. In 2 dimensions, we have a triangle, square, right, pentagon, and so on. We have infinite many. But in 3 dimensions, the Platonic solids, we have only 5. But in 4 dimensions, we have something like 6. In 5 dimensions or higher, we have only 3. So there is a similarity. I don't know whether they are related or not. Anyway, so this is a complete list. Okay. Now, to me, there is an important thing, which is called TKK construction. So named after the 3 people, they independently discovered this. So basically, to each simple Euclidean Jordan algebra, they can construct a simple real Lie algebra. Okay, I will start with this introduction of Jordan triple product. So take 3 elements U, V, W, and we take the product. We have, because of the commutativity, we get 3 possibility. And then one of them, you put a negative sign here, you do this combination. Well, the V is in the middle, so here you put a negative sign here. Okay, this is called Jordan triple product. Now, if we fix W, fix UV, view W as a variable, then we really get endomorphism on this Jordan algebra. Jordan algebra, remember, is a vector space. You map W to this one. And this S, so denoted by S sub UV. And this S sub UV for all possible U and V, that span a real Lie algebra called structure algebra of the Jordan algebra. Because if you do the commutation relation forms a commutator of any two of them is closed. Okay, but here we examine closely. This Z and W behave differently. Remember, we have a canonical inner product on J. So we have vector. We also have covector. But covector, because of the inner product, we can identify covector with a vector called W. And this transformation rule says this Z should be under the transformation of SUV. This Z behaves like a vector, and the W transform like a covector. And here's the UV because this SUV, if we take the adjoint, will become SVU. But then we have to put a negative sign here, to get this co-adjoint operation. Okay, so Z behave like a vector, W behave like a covector. Now, this algebra, structure algebra in general is not, it's never simple. Okay, mathematically, the simple algebra will be simpler. Okay, so they enlarge it, so to make it bigger. So as a vector space, we add one copy of the J and one copy of the dual space of J. And then we can introduce a commutation relation such that this becomes a simple real Lie algebra. Okay, and this commutation relation looks like complicated, but actually quite easy to remember. We have the grading. It's a Z. Z has a grading -1. The structure group, this is like angular momentum, has a dimension 0. This is like a space time, so the dimension -1. This is like momentum, has a dimension +1. So the degree -1, degree 0, and degree +1. And this commutator should preserve the degree. So for example, 2, -1 together should be degree -2, but there's no degree 2 term, has to be 0. Degree -2 term, so it has to be 0. Similarly here, has to be 0. Here, this is degree 1, -1, this is degree 1, so together should be degree 0. The degree 0 should come from here, so some SUV. Why precisely this? Because U behave like a vector, and the V behave like a covector. But by the way, element here can be identified with the inner product with the W. Okay, anyway. So then the only thing not fixed is this normalization. So we don't want to choose to be 0. If choose to 0, it's not simple algebra. Well, we choose to be -2. And this XZ behave like this because Z is a vector, and this Z behave like a covector. So enter SUV will become like this, and this is the original one. So it's quite easy to get this. By the way, this all has a geometric meaning because this simple, this real Jordan algebra has to do with the symmetric domain of tube type. The simplest one, you take a real number as our Jordan algebra, the symmetric domain will be upper half plane, and it's a conformal equivalent to the Poincare disk. And then what would be this conformal algebra? Conformal algebra in this case, well, there's a group here. Basically, the biholomorphic automorphism group of the upper half plane, and then you take the Lie algebra, you get this conformal algebra. Okay. In the Minkowski space-time case, this structural group is really the Lorentz Lie algebra plus the dilation, scaling, and this J is like translation, and this J star is like a special conformal transformation. So altogether, this is a conformal Lie algebra of, okay, in this case. Anyway, oops. Uh-oh. What happened? I don't know why. Or not enough electricity? Lights on, right?
Batteries may be dying.
Oh, battery die. Oh, okay. And then I should have another battery. Uh-oh. Oh. What? Oh. It's nothing to do with battery. I change to a new battery. Oh, maybe I just use yours. Yeah, okay. Oh, okay. But this highlight is not good. Can you see the highlight?
No.
No, that's the problem with the highlight. Oh, okay. Anyway, so I have this, this is called derivation. This is really, for any Jordan algebra, there's something called automorphism group of this Jordan algebra, and it takes the algebra, it's this. For the Minkowski spacetime, this is SO3, our rotation group algebra. And this is the structure group is really the Lorentz group plus this is dilation. And the conformal algebra is really SO4, 2. Okay? And there is something called K, because after all, this has some group there, and the group has something called a maximum compact subgroup. And for that group, I take it as a universal covering. The universal covering would be like this. Okay? So in the simplest case, this would be SL2R, and then the maximum compact group would be the connected one, well, SL. So it's SO2. SO2, you take the universal covering would be R, or something like this. Okay. Okay. Now I want to talk about the generalized Kepler problem. So I will break this construction into two parts. And the first part is the algebraic. There is something called a universal Kepler problem, just like in the vector bundle or calculus classes, there is universal bundle, universal classes. Okay. And the second part is the quantization of a conformal algebra. I will tell you what I mean in the next slides. And in the first part, we write down the universal Hamiltonian in terms of a generator of conformal algebra. And also, I will write down the universal Lenz vector in terms of the generator of conformal algebra. In the second part, we describe a geometric realization for the unitary lowest weight modules. Okay? And so once we have a geometric realization, then elements of the conformal algebra would be expressed as a differential operator. Then you plug it into this universal Hamiltonian relation. Then you will get differential operators for the Hamiltonian, okay, instead of abstract operator, abstract elements in the conformal algebra. So combining these two parts, we get a generalized Kepler problem for each non-trivial unitary lowest weight module. By the way, so-called unitary lowest weight module, the first one who studied, well, in the beginning, this has to do with Princeton. The Bachmann studied this for SL2R, and then Gelfand studied for SL2. Oh, well, for unitary high space, I don't have it. SL2R, the Bachmann, okay. And then there's Harishchandra here, the faculty member here. And he, in the 50s, he found something called a holomorphic discrete series. And it's a unitary lowest weight module for the group I'm talking about. And then he asked, can we find all of them, the classify them? So this would be called the Harishchandra problem in the 55. In the 50s, nobody cares about it. In the 60s, nobody cares about it. And in the middle of the 70s, people start to study it. I guess probably because there's a need to study representation in the 70s. Then towards the end of 70s or by the early 80s, people managed to classify this. Okay, so I would say if we do the Kepler problem, suppose we don't know the result there, eventually we will arrive at the same conclusion. We rediscover the things they found in the 70s. Okay, so essentially say for each non-trivial, well, there's a trivial one we don't have a model. For each non-trivial one, there will be a generalized Kepler problem model. Okay. Now, first, the algebraic part is much easy. The universal Hamiltonian is like this. I cannot highlight. Remember, in the conformal algebra, we have SUV, we have XU, and also YZ, right? And the U and the Z, those are elements of the Jordan algebra. But our Jordan algebra has a special element called the identity element, E. So for this identity E, there's XE, there's also YE. Suppose I formally invert YE and write it as YE to the -1, okay? Then we write this universal Hamiltonian like that. And the universal Lenz vector would be like that, okay? If we take the special one, like a Minkowski spacetime, you plug in, you will get precisely the things we have, okay? By the way, in this case, if you would take U equal to E, the AE would be like 1. That's a trivial one. But what's the non-trivial one is those U which is perpendicular to E. That will be the non-trivial one. That's why Lenz vector in the original case is a vector in R3, not in vector in R4, because the fourth component is always 1. Okay. Now, they satisfy this commutation relation, so we will call the Lenz algebra. Okay. So this part essentially says this LUV is like a generator of rotations. So this Hamiltonian is a rotational invariant in original cases. And this really says the Lenz vector is a conserved quantity. By the way, how do you compute this? Because we know the commutation relation between x and y and SUV, things like that. And remember, YE inverse is the formal inverse. You just remember that, and then you can compute. And this really says the rotational algebra relation. And this really says this AZ is a vector into rotation. And then this is last one is really non-trivial one. Okay. And we have similar things in the original case. Now, this is universal algebraic relation. Now, what do you mean by quantization of a conformal algebra? So by quantization of a conformal algebra, we really mean realizing the elements in the conformal algebra as anti-Hermitian operators on L2 space of function on certain Riemannian manifold. I say anti-Hermitian because we are mathematicians. Physicists usually want Hermitian. Okay. I put a twist there because I allow the case you have vector bundles. Then you talk about the section. The section of vector bundle called twisted functions. Okay. It turns out for each integer k between 1 and the rho is the rank. Remember, I introduced the rank notation. There is such manifold C denoted by ck. Then how about rank over 0? Rank about 0 is really the origin. That really corresponds to the trivial representation, which is not interesting. Okay, we don't. So as a small space, so what is the ck? Ck consists of precisely all non-negative elements of rank k. Say we take the Jordan algebra to be n by n real symmetric matrix, and each of these matrices can be diagonalized, okay, under rotation. And then suppose I talk about non-negative elements. That means the eigenvalue will be either positive or 0, right? And then the number of non-negative eigenvalue will be the rank of the matrix. Okay, so I put these elements together. It turns out they are smooth space. Okay, actually they are structure group homogeneous invariant. By the way, there's structure algebra, and it has something called structure group, and each of these ck is a structure group X on it, and it is a single orbit, so it's a homogeneous space. And since it's a subspace of Euclidean Jordan algebra, and Euclidean Jordan algebra is a Euclidean space, so it's also a submanifold of Euclidean space J. However, I say this ck should be a Riemannian manifold in order to do geometry. Okay, so what are the right metric we need to put on? The right metric turns out to be neither the homogeneous one, homogeneous with respect to STR, and nor the induced Euclidean metric. In order to define the metric, we have to use the Jordan multiplication. Okay, but in any case, this metric, I will call it Kepler metric, is an invariant and automorphism group of the Jordan algebra, because this Jordan multiplication is invariant and automorphism group. Okay, and then in order to get the formula nice, the integration measure we should choose to be the volume. Once we have metric, remember we have volume form. But then we have the rescale by 1 over trace. Trace is just ordinary trace for the matrix. Okay, 1 over the trace of this. Okay, this trace is never 0 because the rank is at least 1. Okay. Now, I should talk about the simplest example. Okay, namely the Jordan algebra is R. So in this case, the rank is 1. The non-trivial k has to be 1. So there's only one ck, namely C1. And the C1 should be the positive element, namely the collection of all positive real numbers from 0. So I call it I plus, so from 0 to infinity. Okay. In this case, the conformal algebra is SL2R, and we don't have the rotational part, structure part. But we have this so-called we do have the structure part. The structure part is only the dilation. This is S. S is the dilation. It's really the Euler operator. And then we have X and Y. The only non-trivial one is XE and YE. And that satisfies this relation. And this relation is precisely the relation, commutative relation for generators of SL2R. Now, this generator will be geometrically realized as a linear operator on this Hilbert space. As we know, this differential operator cannot act on all of them. So we have to choose a domain of definition. Okay? Because I say this commutation relation should be closed, there must be a common domain of definition. And this domain has to be dense. Okay? So we can choose one like this. So, well, first of all, it can be realized like this. This one is really the Euler operator, degree operator, up to a sign. And this y is really multiplication by negative imaginary unit I times x. And this non-trivial one is this one. Okay? Remember, here nu is a quadratic in nu, so there's a symmetry. For two different nu, you could end up with the same thing. But then, as I say, we have to choose a common dense domain of definition for these three differential operators. So it can be chosen like this. So the x to the nu over 2. By the way, x is a positive, so this is well defined. Okay? So this is expansion negative x, and this is arbitrary polynomial in x. And one can check that this is it is a common domain of definition, and it's a dense if and only if nu is a positive real number. And by the way, for 2, there's a symmetry between nu equal to 1. Nu equal to 1 is symmetric. But then it looks like for 2 nu has equal distance from 1, you should have the same operator. But it's not, because the domain of definition are different. Okay.
So what can you do now you have this algebraic structure?
Oh, now next page I will have it. Yeah. Okay. Thank you. Here is basically the representation part. So let me quickly go through that. Then next page I will have it. Okay. So I say it's not hard to see that this operator, a Hermitian operator on this d nu, when nu is in 0 to infinity. Therefore, for each nu, we have a distinct unitary module on SL2R. Okay. One can show that this is really the lowest weight module, GK module. And the K is really the Lie group whose Lie algebra is spanned by this xe plus ye. And then the theorem Harry-Chandra says, whenever you have GK module, you can integrate to the group. So in the end, this pi nu, this Hilbert space, is really give us all possible unitary lowest weight representation of this group. This means the universal cover of SL2R. Okay. There is a classification theorem, and you compare the result, you get all of them. Okay. Now, I come to your question. So consequently, for each nu equal to this, remember we have this h equal to that. But now we realize this as a differential operator, this as a differential operator. Then you just plug in. And similarly, you plug in here. So we'll get an answer. So for each nu between 0 and infinity, there's a generalized Kepler problem whose Hamiltonian is like this. But then we want to solve the bound state spectrum problem. It turns out the bound state spectrum is like this. This I runs from 0, 1, 2. Okay? And this nu over 2. Nu, remember, is a positive. So this never 0. Okay? So the spectrum is like this. And moreover, being a closed subspace because when we solve this problem, our Hilbert space, the wave function, it really lives here. So it's different from the other one. Okay? But then our Hilbert space, bound state, is really a subspace of that. And it is isometric to this one. So it provides another realization. Earlier, for purely representation, we know there's a realization by this one. But now we have a different realization. And that really means we have two kinds of orthogonality condition for Laguerre polynomial. And people know that. One is from mathematics. By definition, they apply Gram-Schmidt process. You produce this Laguerre polynomial. So automatically, they're orthogonal. Another one is you rescale the argument according to the energy level. That's from quantum mechanics textbook. I know some people wrote a paper about this, say, under certain condition, that's the only two orthogonality condition we can have. We don't have the third one. Anyway, so this is a simple example. Then what about the general picture? Okay, so here's the general picture. Okay, for each nu in the W, this W stands for Wallach, because it's Wallach first discovered this kind of set from representation theory point of view. So this W, first of all, there's a discrete part. They start from d over 2, then twice of d over 2, and then 3 times d over 2, up to rho minus 1 multiple of d over 2. Then after that, there's a continuous part. Okay, so the discrete part are equal distance. Okay, for each nu in here, there is a generalized Kepler problem whose bound state spectrum will be like this. Okay, very similar. But here, remember, there's a rho here. In the other case, rho equal 1 in the previous simple example. This really exhausts all unitary lowest wave representation of scalar type. Now, how do we get the so-called other type, so-called vector type? We need to introduce magnetic charge. So by adding magnetic charge, many more generalized Kepler problems are obtained, precisely one for each unitary lowest wave representation of the conformal group. Okay. Let me show you the Hamiltonian without adding magnetic charges. Okay. Remember, on the CK is a Riemann-Manford with some kind of funny metric on it. And so we can write down the Laplace operator here. And this is the Euler inverse square part. But in general, we have to need to add these terms. Okay. Since the K is a discrete, okay, that corresponds to a discrete point in the Wallach set. But then the Wallach starts from somewhere. The Wallach has a continuous parameter. That is because in the case K equal to rho, the full rank case, that people call the symmetric cone. There, any elements in the symmetric cone is an invertible element. You can talk about its inverse. And once you have this inverse, you can use this inverse to continue to deform it. You can continue the deformation. So you can see from this Kepler problem, you can precisely see Wallach things, the parameters. Okay. And then there's a complicated part. This is a Laplace operator. This D means exterior differential operator. This norm means norm with respect to the Riemann metric we have. And then there's this funny function called phi. The phi is a little bit complicated, but we know it's an automorphism J invariant, rational function on J. You have poles. But then it's always a positive on CK. And this phi actually depends on K. Okay.
Are these operators acting on functions on L2R, or what
L2 of the CK.
Of the CK.
CK. L2 of CK.
Sorry, what is the CK again?
CK means a collection of positive elements with rank K.
Okay.
Yeah. Okay. The original Kepler problem corresponds to K equal to 1 case. So it's the extreme end, K equal to 1. The holomorphic discrete case corresponds to K equal to a full rank case. So historically, the Hertzsprung in the other end, full rank case, and the hydrogen atom give you the other extreme, the smallest rank case. But then in between, well, in order people are not connected to each other. Okay, then there's a representation theory of people doing the analytical continuation, start from Hertzsprung to analytical continuation. They have it, but some of the things they are not explicit. For example, they know there's some measure supported on this small CK, abstractly. But in my case, on this CK, I have Riemann metric. I use the volume form, and plus this rho function, phi function, I can write down the measure precisely. So geometric is more refined. Plus, I have dynamics. You can talk about trajectory here. Okay. But I don't. It took me a few months to work out these additional terms. I don't have a geometric meaning. Well, say I don't have conceptual understanding why this term should appear. Okay, I just say it makes the algebra work, so it becomes things like that. Okay, I have 5 more minutes, so I will summarize or make a comment, final comment. So I say they are natural extension of the Kepler problem. I hope you are convinced. Okay. They enrich the already very rich mathematics surrounding the symmetric domain. The symmetric domain, the simplest one is the upper half plane. For each of these Jordan algebra, there's corresponding symmetric domain of tube type associated to it. Okay, and that gives us new vantage point to re-examine Raj-House theta correspondence and unitary lowest weight module. So what is theta correspondence? Okay, I want to mention there's a correspondence here. Remember, we need to add magnetic charge. Once we add magnetic charge, we have a new model. Then we have the Hilbert space bound state. That will be a representation of the non-compact conformal group. But what is magnetic charge in mathematics? Magnetic charge in mathematics, we have to choose a gauge group, which is a compact group, and choose a irreducible representation. So therefore, we have correspondence between representation of a compact group and a representation, even a dimensional representation of a non-compact group. So there is this correspondence. When this group things overlap with the Hall's correspondence case, they agree. It's precise as Hall correspondence. But there are cases which they do not overlap. So you might say this is a generalized set correspondence. So there's a magnetic charge and a Hilbert space bound state correspondence. That is precisely generalization, well, overlap with a set correspondence. And the unitary loss weight representation, which I mentioned, the other side. I came to here, I heard some general talk about Lenz correspondence. They also have some similar spirit. There's a Galois representation, finite dimensional representation, and then the other side, infinite dimensional automorphic representation. And here is also like that. Of course, it's much simpler. And then they provide a baby example for such concept in physics as S-duality, anomaly, and anomaly cancellation. So what do I mean by anomaly? In physics, we know classically we have the symmetry. The model depends on certain parameter. So when we do quantum mechanics, in general, the symmetry won't be preserved unless the parameter be readjusted. Okay. So if you choose a special parameter, the symmetry recover, then we have the symmetry cancellation. So in our Kepler case, the magnetic charge is a representation of a compact group. This compact group has many representations. If you randomly choose one, it won't work. You have to choose certain special one. Then anomaly cancelled. Then you have this beautiful model quantum mechanically. Okay. Then what do I mean by S-duality?
So anomaly cancellations correspond to those fractional values that you had, right?
Yeah.
But at other values you will
It
have.
won't work. It won't work. The algebra doesn't work. Yeah. And S-duality is a really strong and weak duality. This is really, so I would say the Fox from Soviet Union, Fox work is the first example of S-duality, although we don't say it that way. First, S-duality in, well, there's S-duality in topology, basically the generalization of Alexander duality. But the S-duality in the physics first appear in the gauge theory and the string theory. Basically say you have two quantum mechanical systems. Each of them is an interaction system. There's a coupling constant there. And they are isomorphic quantum mechanically. And when you do the isomorphism, you realize if the coupling constant here is small, then the other side will be bigger. Something like that. And in the one side, there's a hidden symmetry. The actual symmetry is bigger, but it's hidden. But on the other side, that same amount of symmetry is explicit. Okay. Now back to the Kepler problem. Why Fox work is like that? Fock really say, because historically we know there's SO4 symmetry and through algebra, and the Fock say, I'm not satisfied with this. I want to see it explicitly, how to see it geometrically, okay, manifestly. And then he said he solved the Schrödinger problem by doing the Fourier transform. And so go to the momentum space and do some compactification. It's not straightforward. There is a certain technical part, okay? So if I later on Moser, the dynamic system, I guess, he realized the classical picture. So if I use the classical picture, essentially it really says this. For the Kepler bound orbit problem, that is equivalent to start with a three-dimensional sphere with radius r. Obviously, there's SO4 symmetry, right? We take a Ronald metric on it. And then you take the geodesic motion. Then obviously, there's a SO4 symmetry. And that dynamics is equivalent to our Kepler dynamics. What? Integrable. Integral and also integrable. Yes, because the sphere is really a symmetric space. Yeah. Okay. And so maybe you ask me. For integrable system, people talk about R matrix things, which I never studied that. But I realized that there are two kinds of integrable systems. One type is you start with a so-called symmetric space, G mod K. Then you do the projection over down to the double coset space, G over K, this side over K, the other side. The shadow here is an integrable system. For that kind of things, we do have a R matrix. And for this kind of superintegral model, I realized there's S-duality here. Basically say, again, you start with this symmetric space. Classically, you do geodesic motion. It's very nice. But then you do something like a S-duality, and sort of Fourier transform. Then see other side. The symmetry becomes hidden, but it's still there. So the Kepler problem is this type. Okay. So finally, I want to say they have interesting connection to algebraic geometry and perhaps even to number theory and fundamental physics. Why to algebraic geometry? In the simplest case, we have this simplest curve, conics. Even in the k equal to 1 case, if we go to other Jordan algebra, it won't be a plane curve. I don't know what it is. So in general, all these curves, I know should be algebraic because the intersection of lots of equations, because the first of this cone set up this algebraic relation, and also this Lenz vector, you set equal to some constant, you set up algebraic equation. Okay. So what are those curves? I have no idea. I haven't investigated. Okay. And why even to number theory? I suspect because by the way, from physics background, I know there are two nice models in the physics textbook. One is a harmonic oscillator. The other is this Kepler problem. Looks like they're different. But in this formulation, the harmonic oscillator, isotropic harmonic oscillators in dimension n, is really a generalized Kepler problem here, associated to Hn of R with k equal to 1 case and scalar type case. So harmonic oscillator is a special type of generalized Kepler problem. And I know in the 60s, Andrew Wei had a long paper relating this harmonic oscillator to theta functions. So presumably, but now this oscillator is just a special case of that. Presumably that work can be generalized. I say fundamental physics because I have speculation, because in the k equal to 1 case, in each case I have magnetic charge. But in the last exceptional case, mathematically you are not allowed to have magnetic charge. But in our world, we don't have magnetic charge observed. So if you want to try to give a theoretic explanation, I say maybe we're in the exceptional case, space-time case, which means 27-dimensional. Okay, that's purely speculation. Okay, so my talk ends here. Thank you. Thanks for the attention.